Yes, my name is Anwar Sounny-Slitine. I'm a geography student in the Department of Geography and the Environment, and a lot of my research and work that I do normally evolves around geographic information systems, so GIS, remote sensing, and modeling the environment. And so now whenever you see my title of my talk, you might be thinking, why does it say solar power potential at UT campus? Well, because I'm using the same kind of modeling techniques that I use with GIS. So whenever I came across my big question, what's the solar potential of UT campus, the first thing I thought about was I'm going to approach this as a geographer using GIS remote sensing. And the thing that I wanted to do was translate these nice maps that I always see of a general solar potential, this is done by the Weber group here on campus, to something that will translate to the campus level to see if solar power, solar potential on individual buildings makes sense. So I'm not like, introducing a new concept. Actually, UT is very proactive at developing solar potential on campus, new buildings like we were talking about earlier with the LEED certification. A good way to get points is to add renewable energy on site. So the building like we're in right now, Student Activity Center, actually uses solar energy for thermal. And then other buildings on campus like the biology building, also the Norman Hackman building also has solar thermal. But solar photovoltaics have been something that's been a little bit more of a challenge to bring to campus. And that's kind of the interesting thing. If we can generate electricity at the building level, that would be really huge. Right now we have a solar photovoltaic system that's just being installed at the parking garage, Manor parking garage next to the UT football stadium. But additionally, we have off-siting of our solar photovoltaic at the Pickle Research Center, where we have the biggest field. So the thing that I'm interested in, though, is that, okay, we have a plan for new buildings. We have a plan kind of in general how to develop, but what are we going to do about our existing buildings? And that's what I wanted to see is, can we harness the solar radiation that hits the rooftops of our existing buildings every day by installing systems on the rooftops? But whenever you start talking about putting solar panels on UT roofs, you always hit the big social barrier of, well, we don't want to cover up these beautiful red roofs that we have. And the one little issue that we have there is that the slanted roofs are going to be the cheapest places and the most potential to install. So limiting to only flat roofs kind of works in some caveats. So I took that into account with my model development. Another issue is the economic barriers. So right now UT generates its own electricity through its natural gas power plant, and it is a very highly efficient, some could say pretty green power system which produces electricity very cheap. And that's putting a solar panel system in that competes with something that you can produce at 7 cents per kilowatt hour is really hard. So that's the economic barrier. So we have two major barriers that are kind of blocking solar development on UT campus. So now to switch to my modeling. So whenever I was going to approach this problem, I started thinking, well, I'm going to treat this like how we normally do elevation models in GIS. So whenever you want to model flooding or even vegetation distribution, which is what I do a lot of work on, we use something called light detection and ranging, LiDAR. So the basic idea is that you have these airplanes that fly over and do 3D scans of the Earth's surface. And this is, they started incorporating this in a lot with the aerial photography that you guys are seeing on Google Earth. So you kind of get an idea of how often it's done, usually like every few years. So what I did was I took this raw data of these this 3D scan, and here you can see an example of it. And this is a elevation model of just the raw data, how it comes. So I took this and I did kind of opposite of what I normally do. Normally I would put break lines around buildings, I would try to filter out trees, and I would just try to make a bare earth elevation model of the ground. Well, instead of that, I kind of flipped it the other way, took out the trees but only extracted out the buildings and made a digital roof elevation model. So the idea is now I know, it's like I went with a GPS unit on top of every building and measured slopes and pitches and angles towards the sun, which you can use later to do a calculation of how much solar radiation hits that rooftop. So making this base map of solar radiation hitting the rooftops of UT campus, you can kind of see what you're working with on how much sun hits our building tops. And like these are all raw radiation numbers. So what you want to do is take these numbers that we're getting here, like the 2,000 gigawatt hours per year, and then multiply it by some kind of efficiency of conversion from radiation to electricity. One interesting result that I found, though, was that while the total roof space in UT campus there's a lot of potential there, even whenever I filter out just for only flat roofs, we still have a pretty good potential in the radiation that's hitting the flat roofs. And then, so that's something that we can think about trying to take advantage of. So I was like, well, start feeling optimistic and good, so let's start modeling this. So I was like, what buildings will we put a solar photovoltaic system on? We're not going to put one on, for example, Littlefield House. Historic buildings, a tower, I don't think is going to be a really cool place to have a PV system. So I filtered out buildings that had either roof space that's being used or if the building had some kind of cultural significance. And I came up with 109 main campus buildings. And I took the assumption that we can get 12% efficiency fairly cheaply. And I made a breakpoint analysis. So what I did is I compared how much money we would save through our electric bills to how much it costs to put solar panels in. And in general, it just didn't make economic sense yet. So what the results came out was that we need to subsidize nearly about 80% of the solar panel if we want to do photovoltaics on campus. You can see here, like PCL, for example, just to explain this map, the green is like the better spots, the reds are not as good as spots. And you can see here, the price there that you're seeing is actually yearly annual return per square meter. I did everything by area calculations. So if you were to say, take that long view like President Powers was talking about earlier, you can take that number and multiply it by 20, for example, to get a good idea. The good news is that solar panels prices are dropping, and in the future we will be able to utilize that with these kind of base maps. Okay, thank you.